So, welcome you all to today's SAAO Colloquium. And today we have Dan Wilkins from Cowley Institute for Particle Astrophysics and Cosmology in Stanford University from California. So Dan had done his PhD from Cambridge with Professor Andy Fabian. Many of you know Professor Andy Fabian because of this iron line work on AGNs and black hole binaries. Dan is more or less working in the similar field and have developed quite extensive models to understand the emission from disk and connection between disk and corona and all. So I will not talk about what he will talk, but definitely many of you are already familiar with his tremendous work on this emission from behind the black hole, which was published recently in Nature.
These are simply symptoms that we're arguing about.
Okay, sorry. Yeah, so basically, let us hear from himself. I mean, he will talk a lot about disk reflection spectroscopy and related things. So now I will ask Dan to share his screen. Please unmute and share your screen, Dan. Thank you. Thanks for accepting our invitation.
Well, thank you, Sunil, for inviting me. It's a real pleasure to be here. And thank you for accommodating me in your schedules as well and shifting the time of your colloquium to fit the time zone I'm currently in on the west coast of the USA. So yes, I'm going to talk to you today about how we can see what's happening just outside the event horizons of black holes and really learn about the extreme processes going on around black holes. In particular, from observations we can make in the X-ray band. So in particular, I'm going to be talking about supermassive black holes in systems called active galactic nuclei, or AGN. Now, AGN are some of the most extreme systems we see in the universe. We think that pretty much all big galaxies in our universe have a supermassive black hole at their center between 10 to the 6 and 10 to the 9 solar masses. And in these active galactic nuclei, that supermassive black hole is accreting material. So there is gas falling into that black hole. And as it falls in through the gravitational potential into the black hole, energy is released, the potential energy is released. And the amount of energy that is released as that gas falls in is enough to power some of the brightest continuous sources of electromagnetic radiation that we see in the whole universe. And so if you look at, say, this Hubble Space Telescope image of the AGN Messier 106, the AGN is down here at the center where that supermassive black hole is releasing this energy. And the energy that's released is powering a light source that's actually enough to outshine all of the stars in the galaxy. Some of these supermassive black holes in systems called radio galaxies are able to launch impressive jets, such as in the galaxy Cygnus A. In this radio image, the actual galaxy is just in this location here. These jets are launched by the black hole in the center, traveling almost at the speed of light. And these jets span far out of the galaxy. And then as they interact with the gas around the galaxy, they inflate these lobes. And we're not entirely clear how jets are launched by black hole, but it's likely that the power source of those jets is actually tapping energy out of the rotation of the black hole itself. And if we add up all of the energy output from the supermassive black hole, whether that's the radiation, the light that's coming out, or the kinetic energy in the jets, we find out that the total energy output of an AGN is comparable to or slightly more than the binding energy that's holding the stars together in the galaxy. And this means that the AGN can actually push away gas that would otherwise fall into the galaxy. So the black hole, in effect, can regulate the growth of a galaxy. This is a process that we call Agn feedback. And we can see it in action in this composite Hubble Space Telescope optical image plus Chandra X-ray image of the giant galaxy in the core of the Perseus cluster. The optical emission shows the galaxy here, and it's got quite an interesting structure with these filaments that come out. But then the X-ray emission is showing the hot gas that surrounds the galaxy. And the black hole in the center of this galaxy is launching jets. And these jets are inflating these lobes, these bubbles in the gas around the galaxy. We believe that every supermassive black hole goes through such an active phase. Therefore, understanding the output of the black hole and how it's releasing energy is a key component in really understanding the formation of galaxies and the structure in our universe. So the big questions we have: how exactly do black holes power some of the most luminous objects in the universe? How is energy released as the gas falls into the black hole? How is that energy output moderated over time? And what are the physical processes that happen around the event horizon that is driving this Agn feedback, this control of the growth of the galaxy on much larger scales? Why is it only some black holes seem to be able to launch jets? And does Einstein's theory of general relativity accurately describe the extreme gravity that's just outside the event horizon? So I'm going to talk today about how we can use X-ray observations of what's happening really in the innermost regions of the accretion disks around black holes to try and head towards answering some of these big questions. I'm going to talk about how we can map the extreme environment just outside the event horizon using the reflection and reverberation of X-rays from the inner accretion disk. I'm going to talk a little bit about how we can observe strong gravity and general relativity in action when we see bright flares of X-ray emission. And then I'm going to talk a little bit about how we can actually measure the properties of the corona. The corona is the source of the intense X-ray emission just outside the black hole. And then finally, I'll wrap up just by mentioning what we're hoping to accomplish with some of the next generation of X-ray missions that are currently in the pipeline. Now, one of the biggest results of the last couple of years has been the first resolved image of the event horizon of a supermassive black hole. This was the image of the accretion flow captured in M87 by the Event Horizon Telescope. We can see the hot ring of gas that's around the black hole. We can see how Doppler shifts brighten the half of the ring that's traveling towards us, so we can see the orbital motion. And most excitingly in this image, we can see the shadow of the black hole itself. So if the Event Horizon Telescope can capture this image, why would we want to find other methods to see things on the scale of the event horizon, such as using X-ray observations? Well, it turns out that the EHT can only actually resolve the event horizon in two supermassive black holes. That's M87 pictured here, and Sagittarius A star, the supermassive black hole in the center of our own galaxy. But we want to understand black holes of all masses. We want to understand how they behave when they're accreting matter at low rates and at high rates. And we really want to understand the full range of processes that can be driven by black holes. So we really need to observe a much larger sample than is accessible by the EHT. When we talk about astrophysical black holes, that's the black holes that we see in the universe, it's useful to think in terms of this cartoon picture. So we have the black hole in the center here, and the black hole is surrounded by its event horizon. The event horizon is the point of no return. So the event horizon is the point around the black hole at which the gravity becomes so strong that nothing, not even light, can escape. So essentially the hole is defined by the event horizon. The material falling into the black hole forms this flattened accretion disk around the black hole. At each radius in the disk, the gas is in essentially a stable circular orbit. And viscous forces and friction in the disk take away the angular momentum from that material. And as the angular momentum is lost, it gradually spirals inwards through the disk. Now, it's useful to think about a characteristic size scale around a black hole, and this is what we call the gravitational radius. The gravitational radius, or RG for short, is gm divided by c squared, where m is the mass of the black hole we're talking about, g is Newton's gravitational constant, and c is the speed of light. And if we think about our black holes in terms of this size scale, it means we can translate a lot of our understanding between different black holes of different masses. We can talk about stellar mass black holes where the gravitational radius is about 1 kilometer, or we can talk about a supermassive black hole in the center of a galaxy or in an AGN, where the equivalent gravitational radius is 1 million to 1 billion kilometers. Now, that event horizon, that point of no return around the black hole, if the black hole isn't rotating, has a radius of 2Rg. 2Rg is also known as the Schwarzschild radius. But if the black hole is rotating as rapidly as we think a black hole should be able to rotate, then that event horizon contracts and it will be at a radius of 1Rg. When we get close to that black hole, we can't use Newtonian gravity anymore. We need to use gravity as described by general relativity. And this tells us that we can't maintain a stable circular orbit at any radius in the disk, but there is in fact an innermost stable circular orbit. The closest you can orbit a non-spinning black hole is at 6Rg, or for that maximally spinning black hole, it's at 1.235Rg. So the picture we have is we have this flat accretion disk of gas swirling around the black hole, slowly spiraling inwards, but only until it reaches this innermost stable orbit. When we get to the innermost stable orbit, the gas will then start plunging very quickly into the black hole. So the density of the disk drops very quickly for these last few radii. Now, the component that lets us see what's going on around the black hole using X-ray observations is the corona. We don't exactly know what the corona is, but it's a population of high energy particles that's formed just outside the black hole. We think that the corona might be heated by magnetic fields that are tied to the accretion disk and tied to the black hole. And as both the disk spins round and the black hole spins round, these magnetic field lines can get tied up. They undergo reconnection events, they release energy, and that's what heats the corona. But then this corona scatters photons that pass through it. So any photons that come from the hot disk, the black body radiation, if they pass through the corona, they get Compton scattered up to X-ray wavelengths. And this is the source of the powerful X-ray emission that we see. Some of the X-ray photons from the corona travel straight to our telescopes, but there'll be some fraction of those photons that shine down onto the disk, and we see their reflection. When the X-ray photons reflect off the disk, they can actually undergo a number of different processes. But one thing that can happen is they can form emission lines from the disk. In particular, fluorescence lines from elements like iron. Now, iron emits a fluorescence line. If we just had a chunk of iron in the lab and we shone X-rays on it, it would emit X-ray fluorescent lines at an energy of 6.4 keV. And for those of you who are used to optical spectroscopy, in X-ray astronomy, we use energy instead of wavelength. So high energy photons are essentially shorter wavelength and low energy photons are essentially longer wavelength. But all of the spectra we'll show will be in units of energy rather than wavelength. So if we had iron in the lab, we would see a line of emission at 6.4 keV. But the iron that we're looking at is in orbit in an accretion disk around a black hole. The velocity of the accretion disk reaches half the speed of light by the time you get to the innermost stable orbit. So that means that the emission lines that we see coming from the disk will be strongly Doppler shifted. The side of the disk traveling towards us will be blue shifted. The side of the disk traveling away from us will be red shifted. But these photons are also emitted deep in the gravitational potential around a black hole. And that means, in addition to Doppler shifts, they experience a gravitational redshift. The closer a photon is emitted to the black hole's event horizon, The more energy it will lose as it climbs out of the potential, the more that photon will be redshifted. Now, this means if we look at emission lines coming from an accretion disk around a black hole, they get broadened out into this characteristic shape. They have a blue shifted peak, and then this extended redshifted wing. And this redshifted wing is made up of the line photons that are emitted from the innermost parts of the disk closest to the black hole. Now, we have two major X-ray observatories at present that are really well suited to observing these broad emission lines and the reflection of X-rays from the accretion disks around black holes. The first is the European X-ray Observatory XMM Newton, which measures the low part of the X-ray spectrum between 0.3 and 10 keV. This is a fairly typical nearby AGN X-ray spectrum measured by XMM Newton. This is a galaxy called IRAS 13224-3809, and we were lucky enough in 2016 to be awarded 1.5 megaseconds, that's 17 days continuous exposure of this one AGN. This is the longest ever continuous observation XMM has ever done of a single point source. But when we see a spectrum like this, we can model it as the sum of different components. One of those components will be the X-ray continuum. This is the emission we see coming straight to us from the corona. And this is essentially just a power law in energy, particularly over the low energy part of the spectrum. And then this blue line shows the spectrum of the X-rays that are reflected from the disk. We can see that broad iron K line. And we also see this excess of low energy or soft X-ray emission. This is made up of a number of emission lines blended together, also coming from the accretion disk. So our reflection has two key components in the low energy band, the iron K line and this excess of low energy X-ray emission. We also see absorption features in our spectrum, and in particular in the iron K band, sometimes these absorption features can reveal the presence of ultra-fast outflows. These are winds that are launched from the inner accretion disk that can travel between 10 and 20% of the speed of light. Then our second tool for measuring X-ray reflection is NASA's NuSTAR telescope. NuSTAR is able to measure the high energy part of the X-ray spectrum from 3 up to about 80 keV. Now, the high energy band is ideal for picking out the reflection from the disk, because in addition to that same broad iron K line we saw in the XMM Newton spectrum, we see this prominent hump in the high energy part of the spectrum that's due to the Compton scattering of photons from the accretion disk. And if we can measure these two components together, it gives us a really good handle on the component of the spectrum that is the reflection from the inner disk around the black hole. Now, we see particularly strong reflection signatures from nearby AGN in a class of Cepheid-1 galaxies called narrow-line Cepheid-1s, such as this galaxy that I'm going to talk to you a little bit about today. It's called Wandswicki 1. Well, one thing we observe about the X-ray emission from these Cepheid galaxies is that their X-ray emission is incredibly variable. We see this constant short timescale variability. It's getting brighter and dimmer, and sometimes the flux we see can double in just a few hours. But in addition to this baseline variability, we also see these transient phenomena in the brightness. We see these peaks and these flares that get launched in the X-ray emission. Now, because the X-ray emission from the corona is very variable, that means the reflection we see from the disk should also vary. The reflection and the emission lines should vary in response to changes in the brightness of the X-rays that are illuminating the disk. But if we observe a variation in the X-rays coming from the corona, there will be a time delay before we measure the variation in its reflection from the disk. And this is because of the additional light travel time between the corona and the disk. And around a supermassive black hole, we're talking about these X-rays having to travel an extra 100 million kilometers, even more. And this means that the light travel time delay can be hundreds or even up to 1,000 or so seconds. And this is something we can actually measure. So this spectrum is again measured by XMM Newton. We've got the energy or the wavelength of the X-rays on the x-axis. But instead of just the flux on the y-axis, what I show on the y-axis is a time lag. So this spectrum is showing whenever there's a variation in brightness, the average time we see each different X-ray energy respond to that change in brightness. And we can see a few features in this spectrum. The energy bands that are most strongly dominated by the continuum. So this is the part of the spectrum between the low energy reflection and the I&K line. This will respond first because the shortest light path is always straight from the corona to us. And then we can see this I&K line that responds much later. We can see a higher time lag for the I&K line. This is because of the extra light travel time from the corona to the disk, particularly at 6.4 keV. The rest frame energy of the line is coming from the parts of the accretion disk furthest from the black hole, where the light travel time is the longest. We also see the time delay from that low energy X-ray reflection. And if we look at the redshifted wing of the iron line, this is coming from the inner disk, which is closer to the black hole. So the redshifted wing of the iron line actually responds earlier than the core of the iron line, which is coming from the outer disk. And we can look at these time lags as a function of the mass of the black hole for a sample of AGN. This was a sample of those low energy reflection part of the spectrum, the time lag there that was compiled by Barbara DeMarco. And this is the time lag of the I&K line as a function of the black hole mass from a sample compiled by Erin Kara. And we can see that the time lag correlates very well with the mass of the black hole. And this is telling us that reverberation is probing a fundamental length scale around the black hole. There's something fundamental about the black hole that is scaling these time delays. And the fundamental size scale that these time delays are probing is the height of that corona above the accretion disk. And we can see that the time delays are very short. The light travel time over between 1 and about 10 gravitational radii. So this means that X-ray reverberation, these time delays, are really probing the innermost parts of the accretion disk close to the black hole. But to really understand these measurements and to be able to interpret measurements of the broad iron line and the reflection spectrum and the time delays we see as a function of energy, the key to understanding those is to build models of the reflection and reverberation process. And this has been a big part of my research, actually since my PhD. I've been building a suite of models that combine general relativistic ray tracing that predict how light travels or X-rays travel in the curved space-time around the black hole. And we can use those to simulate, if we've got a corona, a source of X-ray emission, we can simulate the different paths the X-rays will take to the disk. And we can see in this simple simulation here how the gravitational field bends the X-rays or bends the light towards the black hole, and how the spin of the black hole can cause these photons can get drawn into some orbits here. We then use a radiative transfer code written by Javier Garcia to predict the spectrum of the X-rays that is emitted by each patch of the disk that's illuminated. So we can see that I&K line here that's produced by a piece of iron in the lab. And it's this line that gets broadened out after we apply the gravitational redshifts and the Doppler shifts. And then to apply those gravitational redshifts and Doppler shifts, we then trace all of those rays that are reflected from the disk, all these rays that follow this spectrum from the disk. We follow those rays until they reach our telescope. And again, we have to account for the curvature of space and the curved paths these rays will take. These simulations let us predict what we'll actually observe with our telescope, so we can translate our measurements into measurements of the location and the structure of that corona. We can detect signatures of strong light bending and general relativity in action around the black hole. We can actually predict what the features of general relativity look like in our observations. And we can even start to predict how we'll see the X-rays that come from gas in its final moments as it's plunging into the black hole. So as part of these studies, We were lucky enough to be awarded simultaneous observations of Wandsworth 1, that AGN I showed earlier, with New Star and XMM Newton. And while we were observing Wandsworth 1, we saw that we had the normal variability we see. We saw the X-rays flickering up and down. But then all of a sudden, towards the end of the first chunk of our observations, we got more observations after this. We saw that the corona emitted these series of bright X-ray flares. And when we have these short, bright flares, this is a really good opportunity for looking for the detailed signatures of the reflection from the disk. Normally, we're studying the reflection from all of these small variations put together. So we're sort of averaging it out. But if we see these bright flares, we can look for the reflection from the disk, the echo from the disk, in response to just a single flare. So what we want to do is really take a close look at this flare and look at the different energy bands that correspond to the ion line that's emitted from different parts of the accretion disk. So what I did here is I've actually taken these two flares and I've stacked them on top of each other to add them together. And then I show the light curve of this combined flare in these different energy bands. First 1 to 3 keV, which is mostly just the continuum emission we see coming straight from the corona. And we can see this overarching shape of the flare here. This will have a few of the most extremely redshifted ion line photons from the very inner part of the disk in this band as well. And then I look at the light curve in the 3 to 5 keV band. This is the redshifted ion K photons that come from the inner parts of the disk. Then 5 to 7 keV, which are the unshifted ion K photons from either the bit of the disk that's traveling in front of us or the outer disk. And then the 6 to 8 keV photons, which are the blue shifted ion K line photons from the inner parts of the disk that are traveling towards us. And what's interesting here is on top of the overarching shape of the flare, we see these additional short timescale peaks in the emission. So some of those peaks appear at the same time in all the energy bands, and that is just flickering of the corona. The corona emits its spectrum over a broad range of energies. So simultaneous variation in all the energy bands is just short timescale flickering of the corona. But then we also see this series of peaks that are offset in the different energy bands. They appear first in the blue shifted ion line photons, and then later in the red shifted ion line photons. And then we see a subtle hint of this peak in the most extremely redshifted photons. So we see these almost echoes of the X-ray flare, these echoes of the flare that appear as the primary flare is fading away. Now, these peaks, these echoes are significantly detected. There's less than 0.01% probability that they appear either due to Poisson noise or just to the random red noise variations that we see in the light curve. So what are these different echoes of the flare that we see at different times in different energy bands? Well, to interpret that, we turn to our theoretical model of the echo of a single flare from the accretion disk. So what I show here are the ion K line photons we expect to observe as a function of time after a flare. Now, the Doppler shifts and the gravitational redshifts from different parts of the disk are different. So that means as this flare echoes off of different parts of the disk, the photons we see at different times are shifted to different energies. So these line photons were originally at 6.4 keV, but they're now spread out. And all of these photons put together are what form that broad emission line that I showed before. Now, the first response we see from the disk corresponds to the energy shift of the photons that come from the part of the disk for which the total light travel time from the corona to the disk to us is the shortest. So that's the part of the disk we see responding to the flare first. And that will be a patch of the disk, not quite on the inner edge, but it'll be a part of the disk that's right in front of us. So we see the photons that go down to this part of the disk, get energy shifted, and then come to us. The latest photons we see are the ones that come from the very outer parts of the disk. And because the gravitational field is weak a long way from the black hole and the motion of the gas is slow, there's not much energy shift on the photons. So the photons we see at late times gradually converge on the 6.4 keV we expect from a piece of iron that's stationary. But just after the first response, we see a slightly later response from the most blue shifted and the most red shifted photons. This is the innermost part of the accretion disk, the most red shifted photons on the side traveling away from us, the most blue shifted on the side traveling towards us. But these photons have to climb out of the gravitational field. And as these photons travel through the strong gravitational field around the black hole, their passage gets delayed. So that means the parts of the disk closest to the black hole, we actually see their response delayed after the first response we see. And this time delay is extreme from the inner disk, so the most extremely redshifted photons also have extreme time delays. But an interesting feature of this plot is you can see after we see this first response of the blue shifted and the red shifted photons, this first track, we also see this second track of blue shifted photons first and then red shifted photons at later time. You see how there are two responses of the blue shift and the red shifted photons. And this second track, this second response, are the reflected iron K line photons that are coming from the patch of the disk that's behind the black hole. Now, classically, this part of the black hole should be hidden from us because no light should be able to pass through the black hole. But we can see the photons that are emitted by this patch of the disk that should be hidden behind the black hole because these photons are bent around the black hole. So they travel around the black hole and into our line of sight. And we can use this model to predict the light curves that we measure. So these are the light curves of the flare in those different energy bands, just by summing up all of the photons as a function of time in these different bands. And we can see that this re-emergence, we call it, these photons coming from the backside of the disk, lead to these sharp peaks in the light curve. First in the 6 to 8 keV band, later in the 4 to 7 or 5 to 7 band, and then later still in the 3 to 5 keV band, and then much, much later from those most extremely redshifted photons at 1 to 3 keV. And the reason these echoes from the backside of the disk appear as such a sharp peak is because the emission from the backside of the disk is actually magnified by gravitational lensing as the rays propagate around the black hole. We can actually fit this model to the light curves that we observe, and we find that this model fits the relative timing of those echoes of the flare very well. Not only that, but parameters in this model describe the mass of the black hole and the height of the X-ray source above the accretion disk. And so we can use this model to estimate the mass of the black hole and the height of the corona above the disk, and we get more confidence that this model is correct and that these peaks are the echoes of the flare from the backside of the disk hidden behind the black hole, because we note that this mass estimate we get from the model and the height of the corona we get from this model agree very well with measurements we can make of the mass and the height by independent means. There are other measurements we can use to get similar values of these two parameters. And then lastly, and then instead of looking at the light curves, we can actually look at how the reflection spectrum varies as a function of time. So this plot here shows, first of all, this is just the shape of the two flares for reference. So we can see the relative timing with respect to the flares. But then down here, what I show is the spectrum in each time bin that we observe. So at each time, the shading corresponds to how many photons we see at different energy. But what I've done here is I've subtracted from each time bin the power law that best fits the spectrum. So by subtracting this power law, we take away the continuum component. So what we're left with here is just the spectrum of the variable reflection from the disk. And we can see at the times corresponding to those echoes we saw, shown by the white box here, we can see that loop and that waterfall feature that we saw in the theoretical model of X-ray reverberation starting to appear out of this noisy data. And we can actually see this same reverberation signature is repeated as the disk continually responds to variations in the X-ray emission from the corona. So I can just summarize this with a quick animation. What we're looking at is a bright flare of X-ray emission. And then at each time after that flare, we're seeing the emission from different parts of the accretion disk. And the emission from each part of the disk is identified by the specific energy shift, the Doppler shift and the gravitational redshift we expect from that part of the disk. And this echo from behind the black hole corresponds to these frames of the movie, when we first start seeing the response from the backside of the disk. And in these images, the backside of the disk is this loop feature here. And this is because of the gravitational lensing and the light bending, the backside of the disk appears above the black hole because those rays are being bent around the black hole into our line of sight. So this is the moment in that movie when we first see the reflection from the backside of the disk. So with these observations of reflection from the inner accretion disk and the time lags between the continuum and the reflection and the echoes of X-ray flares from the accretion disk, how can we actually use them to map the environment around the black hole and learn about what's going on there, specifically the corona? And this has been another big component of my research, bridging the divide between theory and observation to translate these measurements we have from X-ray observatories into maps of the corona and of the inner accretion disk. Now, X-ray reverberation is the ideal tool for mapping the inner disk because we have two measurements we can make. When we have photons that are emitted at a known energy, such as that iron K fluorescence line from the disk, the shift in energy that we observe from those photons by the time they reach our telescopes tells us about whereabouts on the disk they are emitted. This is the combination of the Doppler shifts and the gravitational redshifts. But then we can measure the time delay in each of those energy bands. The time delay in each energy tells us how far away each bit of the disk is from the patch of the corona that illuminated it. So by piecing these measurements together, we can start to build up a three-dimensional picture of the inner disk and the corona. The first measurement we can make here is just from the shape of the iron line itself. This redshifted wing of the line comes from the emission at different radii on the inner disk. So what we can do is we can take the shape of the line we observe, we can fit it as the contributions from different parts of the disk. And this in turn tells us how bright each radius on the disk is, even though we're not able to spatially resolve an image of the disk. So we can reconstruct an image. Now we find that the inner part of the disk is very strongly illuminated. The reflection is very strong on the inner disk and it falls off very quickly. It's essentially a power law following about r to the -8. And this is because of the strong light bending towards the inner disk and the blue shifting of photons as they travel to the inner disk that enhances the reflection from the very inner parts. We also see that the reflection intensity levels off over the middle range of radii in the disk. So after it falls off steeply, it then remains constant for a while before falling off over the outer disk. And this flattening of this profile, where the reflection remains at a constant intensity over a range of radii, tells us that part of our corona is actually extended over the inner parts of the disk. So we can measure that in many AGN, the corona actually extends around 10 gravitational radii over the inner parts of the disk. And just to show here, what we're essentially doing is reconstructing this image of the accretion disk from how much reflection we see at different radii. And the next thing we can do is we can measure those time delays in the different energy bands, those different parts of the iron K line. So here's a theoretical model of the time delays we expect if our X-ray corona is just a tiny point above the black hole. We can see the delayed response of the ion K line from the outer disk here. We can see the delayed low energy X-ray reflection here. And we can see that redshifted wing of the line. This is the line from the inner parts of the disk, closest to the black hole and the corona, closer than the outer parts of the disk. So the redshifted wing of the line responds sooner than the core of the line from the outer disk. But what's important about these models is the earliest response we should always see, the shortest time, will always be the energy band that's most strongly dominated by the X-ray continuum coming straight to us from the corona. The light path from the corona straight to us is always the shortest. And this should always be between 1 and 2 keV. But unfortunately, this is not what we observe in real AGN. In nearby Cepheid galaxies, we actually find that it's not the 1 to 2 keV band, which is strongly dominated by the continuum that responds first. It's the 3 to 4 keV band, which should be the redshifted wing of the ion line. So somehow we've got the X-rays reflecting from the inner accretion disk. They're actually overtaking the emission we see coming straight from the corona. And that is inconsistent with these simple models of either a point-like corona or a corona that's extended over the inner disk. However, one thing my collaborators and I actually figured out is that if instead of having a point-like corona or a corona associated with a disk, if our corona is vertically collimated, and every time it brightens, the brightening starts at the bottom and the fluctuation propagates upwards. So we kind of have an X-ray source that looks a little bit like a jet or a failed jet, because a lot of these AGN we're looking at are radio quiet. They don't have strong jets. But if we have an X-ray source that looks like a failed jet, we can actually produce this pattern of time lags that we see. Because in this scenario, the lowest part of the corona brightens first, but the photons that get emitted from the flare when it's at the bottom of the corona, all of those photons get lensed towards the black hole and bent down onto the inner disk. So we don't actually see any direct X-ray continuum emission from the lowest parts of the corona. So that means the earliest response we see is indeed the 3 to 4 keV ion line from the inner disk. And in order to see the change in brightness of the continuum, we have to wait until the flare has got high enough up the corona for the rays to be able to escape and travel straight to us, which is why the continuum responds at this time indicated by the red line, which is later than the response of the redshifted part of the ion K line. But now we've got two different pictures of the corona. From the shape of the ion line, we said that the corona was extended over the inner accretion disk. But from these timing measurements, it looks like we've got a collimated corona that looks like a failed jet. How can we have both of these pictures? Well, the answer is that the corona seems to actually be formed of two components. And what we find is that we only see this 3 keV earliest response if we're looking at the response times to rapid changes in brightness. If we're looking at the slow components of the variability, we find that actually the time lag is the lowest between 1 and 2 keV, consistent with the disk corona. So we have this picture that the rapid variability we see in the X-ray emission is coming from this collimated core of the corona, which could be a failed jet in these radio quiet AGN, a jet that has collapsed on itself. It's not able to escape the galaxy, but it dissipates all of its energy very close to the black hole. And we actually have electrodynamic models that show that this can be possible. And then the slow variability in the X-ray emission comes from the inner parts of the accretion disk. I mean, it's likely that the inner accretion disk is magnetized. We think we need a magnetic field there in order to take the angular momentum away so the gas can actually move inwards. This is called the magneto-rotational instability, or MRI. And if this magnetic field undergoes reconnection above the accretion disk and dissipates energy above the disk, it can quite naturally produce this component of the corona above the inner accretion disk. So we're piecing together this picture from our reflection and reverberation measurements that actually the corona is these two components. And actually, a collaborator of mine, Yaji Yuan, working with Andrzej Spitkovsky and Roger Blanford and I, Yaji was leading these electrodynamic simulations of magnetic fields we expect when they're tied to a spinning black hole with an accretion disk around it. And what she found is that the rotation of the black hole causes the magnetic field to open up, and this is what can launch a jet. But if our accretion disk has too strong a magnetic field associated with it, it can actually form an instability that causes the jet to collapse. And then when this jet collapses, it constantly undergoes reconnection events with the magnetic field from the accretion disk. So then the currents that are driven here dissipate energy. So if we have too much magnetic field from the disk, it looks like we can cause a jet to collapse. And this is what can cause that compact collimated X-ray source, when all of that energy that would go into the jet gets dissipated close to the black hole. And we can use these reflection and reverberation measurements to actually trace the changes in the corona over the course of those bright flares. And then we actually discovered, in two different AGN now, that it looks like when we get those bright flares, the corona gets gathered up, it gets launched away from the black hole like a failed jet launching event. And then it can't sustain this jet. So then the corona collapses down again to this very confined region around the black hole after the flare. So what are our next steps in reflection and reverberation studies of supermassive black holes? Well, it'll be important to study a broad sample of the supermassive black hole population. And the black holes we've been focusing on have primarily been the nearby Cepheid galaxies, because they show strong reflection signatures from their accretion disk. They're nearby, so that means they're the easiest sources to study in detail. We get a close-up view of the processes that are happening right around the event horizon that are driving accretion and powering the corona. But most of these nearby AGN don't launch powerful jets, and they're probably not actively governing the growth of their galaxies. So we really want to extend our sample. I've been working on techniques to extend these time delay reverberation measurements to radio galaxies. And if we can measure the X-ray corona in a radio galaxy, we can understand how the corona is related to the jet and start to understand why it is some black holes are able to launch jets while many don't. And then in terms of understanding Agn feedback, we really want to look at high redshift black holes. We want to look at the massive black holes that are rapidly growing. And these are going to be the supermassive black holes in the quasars that launch powerful winds, and they have a strong influence on their host galaxies. The one thing that Rubens Rees and Don Walton and Mark Reynolds discovered is that using Chandra, the US X-ray observatory, where quasars are magnified by gravitational lensing, so this is the Einstein cross, it's a single quasar that gravitational lensing has produced 4 images of. We can actually see the ion line coming from the inner accretion disk in this lensed quasar. So by understanding what's going on close to the event horizon in this quasar, we can actually start to understand how black holes are growing, and we can see the actual processes in action that are driving that Agn feedback and governing the growth of galaxies. And this is actually a really exciting time for X-ray astronomy. We've got a couple of new missions coming down the pipeline over the next decade. Just in the next couple of years, the Japanese Space Agency, along with collaboration from NASA, are going to launch an X-ray observatory called XRISM. XRISM carries a new type of detector, which is a microcalorimeter array that gives us extremely high resolution spectra, or almost 2 orders of magnitude higher spectral resolution than we currently have around the INK line. And this will transform our measurements, in particular of how winds that are launched by accretion disks are related to the corona, and the role that winds and outflows play around black holes. And the next big flagship X-ray observatory will be called Athena. I'm actually part of the team at Stanford that's developing the readout electronics for the wide field imager detector on Athena. We're hoping to launch Athena by 2034, and this will be the next flagship X-ray observatory. It will have an order of magnitude more collecting area than XMM Newton, which is the current state of the art. And this will give us breakthrough capability in precision, spectrum, and timing and time delay measurements. So we can zoom in right on that inner region around the black hole where the gas is actually plunging into the black hole to really test general relativity and understand the corona. And Athena will have the sensitivity to study black holes in the distant universe to understand black hole growth and AGN feedback. And then we have a couple of missions in the X-ray band that have been submitted to the US Decadal Survey, which we're hoping to get the results of in the next month or so. But we're hoping the Decadal Survey will support one or more of the X-ray mission proposals. And these include STROBE-X, which is a specialized high precision, large collecting area mission for measuring timing and time delays. This will be particularly good for measuring time delays around smaller stellar mass black holes that we can't really do at the moment. And then LINX will be the next flagship US X-ray observatory, we hope, if it gets support from the Decadal Survey. And this will combine the collecting area with Chandra, the collecting area of Athena with the angular resolution of Chandra. And this large collecting area, high angular resolution, is what we really need to study the first black holes that formed in the universe and to really study how black holes govern the growth of the galaxies they live in. And so to summarize, X-ray reflection and reverberation are letting us probe structure right down to the innermost stable orbit, and they're letting us map out the corona and the inner parts of the disk. During those bright X-ray flares in Wandsworth 1, we saw general relativity in action in the extreme gravitational field. We saw the re-emergence of the echoes of X-ray flares from behind the black hole, as predicted by the theory of general relativity, as that emission gets bent around the black hole into our line of sight. Reverberation is revealing for the first time the actual structure of the X-ray corona. We're starting to see evidence of a persistent collimated core, somewhat like the base of a failed jet in a radio quiet AGN that's embedded within this extended part of the corona of the disk. And these are huge advances we've made with XMM Newton and NuSTAR and also Chandra and Suzaku, but we've got much more to look forward to with CRISM and Athena and fingers crossed, STROBE-X, LINX, and many more missions. So I'll stop there and I'm happy to take any questions. Thank you.
Thanks a lot, Dan. It was really very nice journey through. And I'm pretty sure that many of the attendees will have some questions. And before I ask mine, I will invite Hermit. Please unmute and ask your question yourself, please. Go ahead.
Yes, hello. Yeah, very nice. I'm going to ask a devil's advocate question.
Sure.
We showed your light curves earlier on and where you were pointing out various peaks and saying there's delay of the one or the other, but there's quite other peaks as well.
Yes.
I know that these are really, those are peaks are related. And the other question, maybe I should come in, is because I've observed some of the same objects in the optical, and whenever we get alerts that there's very interesting things happening in X-rays, and we happen to look at the spectrum, we always find there's practically no change at all. Can you maybe comment on why this always seems to be that whenever something's happening in the X-ray, you basically don't see much in the optical?
Yeah, sure. So to your first question, yeah, that's actually a really important comment you've picked up on there. And unfortunately, in just the time I had today, I didn't have time to go into all the details of the analysis. But you're right. There is a lot of variation and a lot of short timescale peaks that go on in the light curve because we're fundamentally not looking at just a single isolated X-ray flare. We're looking at this constant stochastic variability of the corona. So the way we pick out those, so actually there's actually two sides to this. So actually the first thing we do, when we do a lot of the reverberation measurements, when we're measuring the structure of the corona and the time delays, we actually don't just look at a single flare. We're actually using all of those peaks in the light curve. And we're doing it the equivalent of a cross correlation, but with Fourier transforms. And so we actually use those, every one of those short peaks, that all those variations go into the analysis together. Now, in terms of the echoes of the flares around the black hole, we actually did a lot of statistical tests on those flares that we identify with the echoes. So the probability that I quoted, the significance of less than 0.01% chance of them sort of being spurious signals, actually takes into account all of those other little flares that are going on. We do an analysis of the variability we observe over the whole light curve and work out how common each of these events is, particularly how common they are when they're uncorrelated, when they appear at different times in the different energy bands. So there's a lot we have to put into that analysis, but yeah, you're completely right there. And then in terms of the optical variability, that's actually one thing we don't fully know the answer to that yet. And this is something we've observed ourselves as well. I mean, some of the studies we've done of bright X-ray flares, we've discovered the flares using SWIFT, where we do weekly monitoring also of an AGN. And that means we've got these years-long light curves of X-ray and optical and UV variability. And sometimes there are big peaks in the X-ray emission that do appear in both bands. But as you said, most of the time, the optical seems completely disconnected. I think the reason for that in part is because when we're looking at the optical and the UV emission, we're looking on a much larger scale. So the shortest wavelength UV we can observe with SWIFT, this is the UVW2 band, is coming from a radius of about 100 gravitational radii in the accretion disk. And then the optical bands will be hundreds to thousands of gravitational radii in the accretion disk. So we're not observing in the optical and UV the very inner parts of the disk. So a lot of that disconnect, I think, could come just because of if the variability that's being generated in the X-ray emission is coming from what's happening on the very inner disk, whether it's these chaotic magnetic fields reconnecting or if it's the turbulence on the inner disk. We're just looking at a size scale that's an order of magnitude smaller than we're able to see with the optical UV. So I think the variability is getting generated much closer to the black hole.
Okay, thanks.
Yeah, great. Do we have any other question? I don't see any hand raised. Okay, so then I can take this opportunity to ask my question. In fact, when we started learning this reverberation mapping during our coursework, we came to know, I mean, we read that the small deformation in the iron K alpha line can discover a lot of information about things happening close to black hole. And thanks that your model is taking care, I mean, using those little deformations to generate a 3D map around the black hole. It's really great work. And what what I see fascinating is like the role of magnetic field. I want to know that what will be the kind of magnetic field, what kind of expected magnetic field for having this kind of collimated vertical corona or point-like corona, or it's like a, what kind of magnetic field morphology, or in terms of like what kind of strength, magnetic field strength you expect? Can you comment on that, please?
Yeah, sure. So the best place to look actually is Yaji Yuan's paper with where she put these simulations together. I'm afraid I don't have sort of magnetic field strength numbers off the top of my head here, but I think the interesting part here is the structure of the magnetic field that that might lead to these different forms of corona. So the real key features that we saw here, because I mean the whole driving force behind this work was there'd been these talk of these lampposts and sort of point-like X-ray corona for a while, that were sort of more a phenomenological model to interpret the observations. We were interested in, could we ever predict a point-like corona or a compact corona close to a black hole? So that's what really spurred on the simulations, and I think the natural field geometry you expect around the spinning black hole is this sort of jet-like geometry, because the rotation causes the field lines to be opened up. But in order to get the X-ray source close to the black hole, the key thing we sort of need here is some way of dissipating this, because when we have the large-scale jets, we think that these magnetic fields are largely uninterrupted out to large radius, which means they don't dissipate much. Most of the jet, when it's close to the black hole in a radio galaxy, we think most of the energy should be in the electromagnetic field at that point, and it's not until we get to larger radius it starts getting dissipated and we start seeing the radio emission. But what we need, the key feature we need here to really produce this corona is some dissipation mechanism, and it looks like the way that happens, at least in these simulations, is when we get an instability that's generated. So the magnetic field morphology here is you get the jet-like structure, but then you have the vertical magnetic field coming from further out in the accretion disk that's putting too much pressure on the inner regions if there's too much field from the disk. And then that causes the kink instability essentially to develop. And then that's what causes the jet to fall over. So I think it's really the instabilities in the magnetic fields that are really the key to getting this X-ray emission. I mean, simulations have shown for a while now that you can produce magnetic fields and then you get dynamo effects that amplify the field. But it's these instabilities that are really key to getting the X-ray corona to actually dissipate the field.
Oh, great. Yeah. So, and another thing is, like you were saying, that the base of the jet is always the corona in a black hole.
So actually, the jury's a bit out on when you actually do have a jet. So there's actually been a few papers recently by Shifan Zhu at Penn State, and he's actually discovered, and he's been doing population studies of radio loud AGN, particularly the radio loud quasars, and looking at the relationship between the X-ray emission and its variability across that sample. And it actually appears that the radio loud quasars and the radio quiet quasars have very similar X-ray properties. So it looks like the corona exists regardless of there being a jet. It looks like the corona is separate from the jet. What we show here is in the radio quiet object, we can have the jet fall over and produce an additional X-ray corona. But I think the evidence at the moment, though, is even when there is a large scale jet that's not dissipating, there's still a corona there that exists separate to the jet, which is likely coming from the disk, I think, as well.
Oh, great. Thank you. So since the time is already up, but anyway, we can have one or two more questions if there is any from participants. Please raise hand. Okay. Any comment? Okay. Okay, and then I think it was really informative, much more informative for everyone, just like me. I'm really happy to have you with us for today's colloquium, and it was really tremendous journey. Thanks a lot, and best wishes for your future work.
Yes, so thank you so much for having me. It's been a real pleasure to be able to join you today.
Yeah. Bye.